I'm from Osaka University in Japan. Today I'd like to talk about our paper, a surface modeling method for indoor spaces from 3-point cloud, reconstructed by 3D Gaussian splatting. This is today's outline. First, I'll talk about the background of this research. Building information modeling in an architecture project is expected to be utilized not only during the design and construction phases, but throughout the entire building lifecycle, including maintenance and management. However, while adoption of BIM data in new construction projects is advancing, there is a lack of BIM data in many existing buildings, where the efficiency of maintenance and management is a priority. The common method for BIM conversion of existing buildings is called scan-to-BIM, which involves acquiring point clouds through laser scanning or photogrammetry and constructing BIM models from the obtained data. Laser scanning provides precise point cloud data, but it requires expensive laser scanners. On the other hand, photogrammetry generates point clouds from images, making it a low-cost option, but the accuracy of the point cloud data tends to be lower. Here we focus on cost-effective image-based 3D reconstruction methods, such as photogrammetry. Image-based 3D reconstruction methods, typically represented by photogrammetry, have recently gained attention with machine learning-based approaches such as NAF and 3D Gaussian splatting, which have successfully generated high-quality 3D scenes from 2D images. Therefore, we consider whether it would be possible to create 3D models of the indoor spaces of existing buildings using a new 3D reconstruction method instead of relying on traditional scan-to-BIM techniques like laser scanning and photogrammetry. As for the previous research, there has not yet been any research conducted on creating BIM using 3D Gaussian splatting. Hashizume et al. Are investigating the feasibility of NAF BIM, but now faces challenges in terms of data accuracy and processing speed, especially for large-scale or complex scenes. Therefore, we considered whether 3D Gaussian splatting, which achieves similar quality to NAF, but with faster processing, could be a viable alternative. Additionally, Wei et al. Proposed a method for semi-automatically creating 3D wireframe models from precise point cloud data obtained by S3DIS dataset. We wonder if this method could be applied to point clouds generated by 3D Gaussian splatting. Therefore, the objective of this research is to use 3D Gaussian splatting as an alternative approach to traditional scan-to-BIM to create surface models, including floors, walls, and ceilings, that form the basis of BIM data for indoor spaces. Second, I'll explain our proposed system. Here is an overview of our proposed system. For simplify, we have chosen rooms where the walls are perpendicular to the floor and ceiling with a constant height, and the shape of the floor has straight boundary lines with all corners at right angles. This system follows three main steps. First, multiple view images of the target indoor space are prepared, and point clouds of the target space are generated using 3D Gaussian splatting. Next, pre-processing of the generated point cloud is performed. And finally, geometric and numerical information is extracted from the point clouds to create surface model. Let me explain a little bit about 3D Gaussian splatting. It's a technique for reconstructing three-dimensional space from multiple images, and it increases the initial point cloud during machine learning. In this example, about 340,000 point clouds were generated from 110 images. We used the newly generated point clouds with this method. Next section is partition and discussion. I briefly explain each step. In the first step, images of the indoor space are taken from multiple viewpoints using a camera, and these images are used as input for 3D Gaussian splatting. It is assumed that there are no objects in the room when taking the pictures. Next, in the pre-processing of the point cloud, we performed rotation processing and noise removal. 3D Gaussian splatting generates point clouds with random rotations, so it is necessary to rotate the point clouds to align them with the real-world coordinate system. In addition, as point cloud generated by 3D Gaussian splatting contains a lot of noise, we used two noise removal algorithms, statistical outlier removal filter and density-based spatial clustering of applications with noise, available in a Python library called Open3D to remove this noise. In the final step, after classifying the point cloud based on height, we carry out Fukuda shape estimation and output the surface model using IFC OpenShell Python. Also, because the point cloud generated by the 3D Gaussian splatting follows the scale of budget space, we used an object of known length as a reference during capture and performed scale conversion before outputting the surface model. In the verification process, we compare the measurements of the actual indoor space with the dimensions of the surface model created by the proposed method. In addition, we used IOU to evaluate the overlap rate and overlap rate of the floor area. The results of applying the same procedure to another room B are as follows. The results are as follows. As shown in the image on the left, the floor area of the created surface model was rescaled and overlaid with the floor area based on actual measurements. In this case, we were able to create a surface model that is relatively close to the original shape, but the maximum error for each side of the floor was 0.574 meters. It is considered that sink, which appears as an obstacle in the input images, prevented accurate acquisition of the ground point cloud. On the other hand, in room B, the shape of the framed area in the left image was not accurately created. The most likely reason for this is that many of the input images had this area blocked by a wall. As a result, it is so that the point cloud for this area could not be acquired accurately. In addition, the height error was 36 millimeter in room A and 66 millimeter in room B. Compared to the height error of the indoor space, the error range for each side of the floor is larger. Overall, it can be concluded that the accuracy is significantly inferior to laser scanning. Now let me summarize my talk. We propose a method to create surface model which serves as a precursor to the BIM model of existing building in the spaces using point cloud generated by 3D Gaussian splatting. We confirm that the created surface models have errors in the range of around 0.01 meter to 0.5 meter, indicating potential issues during the point cloud acquisition stage. In the future, the challenge is to create surface models with accuracy comparable to laser scanning. 3D reconstruction methods like 3D Gaussian splatting are still relatively new technologies, so there is potential for accuracy improvements. It also has the advantage of being much more cost-effective than laser scanning. If accuracy improves in the future, it could be possible to accommodate different types of the indoor spaces in the same way as laser scanning methods. I'd like to close my presentation. Thank you for your attention.
Yeah, thank you, Keiji. if you're looking for a demonstration building in the future, I would advise to take this building. So it has quite some curved walls, and I think this will really be a good test bed. Any questions? Yes.
Yes, I wanted to ask you, first of all, really nice presentation. What software did you use for when you imported the images? Like, I mean, usually I use Metashape for photogrammetry, but how do you generate the 3D Gaussian splatting from the 110 images you said you used as an input? So how did you process them? What software did you use? And what method, like, how?
Thank you.
Here.
Yeah.
Oh,
Yeah.
yeah. Oh.
Yeah, these are 110 images you said. Yeah. I was wondering.
First, we capture images, and next process is structure formation. So 110 images.
So that's the name of the package.
It's the Gaussian splatting.
Is the name of the tool? Okay.
It's available on GitHub.
Okay.
Mm-hmm. That was your first question.
Yeah, the second one is you showed also the number of points you cleaned and then you classified. And I was wondering if it was possible to get additional points, like to get much more points. If you go to the
could you please?
Here, yes.
Here.
Yeah. So the noise field. Okay. And then you use like segmented. Okay. So was it possible to get more points, or that was the amount that the maximum amount of points you can get from Gaussian study? The maximum you can get.
Yeah. But the Gaussian splatting is very much noise. So wait.
But what you were saying is you would first filter and
Yeah,
then
after
have
the
points
filtering.
and filter and.
Yes. So if it's possible after the filtering to get more points. That's the question. Yeah.
The good points, not the bad
Yeah,
points.
yeah, to get the good points, exactly. Yeah, that's what I mean. Not to eliminate the points as you said before, the obstacles and all this, to get this data that you want. That's what I mean.
We couldn't classify good point and bad point because it's very complex. Very complex point cloud position.
Okay. Yes.
So this time we use XOR filter and this.
Okay.
Okay, the good, the bad, and the ugly points. Great. Well, there's one more question, a second one, so.
Okay, thank you. I have a couple of short questions. Maybe at first, how long did it take to calculate out of the images the 3D model?
This example generation time is 3 minutes and 39 seconds. But in case of NAF, generation time is more than 1 hour.
Okay.
1 hour or 1 day to 1 hour to 1 day.
Yeah.
Okay.
And what kind of space is it? Is it where the criminal police is operating, and or what is happening in this space? It's from a criminal series in television. No. No, it's not the office of the president. No, you don't have a president. It's not a tenor, so to say, his private room, huh? No.
No.
Okay.
So to verify the accuracy of the 3D reconstruction, so we select the back-end rooms.
Okay.
Yeah.
Yeah.
Thank you.
So there's one question and one more. So.
Well, it was a similar question in terms of speed. I mean, you said that the 3D Gaussian splatting is inferior to the accuracy that you get from kind of laser scan method.
Yeah.
Is there any benefit to actually using 3D Gaussian splatting? Because from what I understand, they mainly use it for images in movement.
Yeah.
So, you know, autonomous driving or similar. So what are the, you know, you talked about the disadvantages, what are the advantages, if there are any?
We think the Gaussian splatting, the benefit is this time only cost effective than laser scanning. This time only cost effective. But this technology is opened last year August. So new technology. So evolve.
So you expect it to improve
Yeah.
over the next years? Okay, thank you.
One more additional comment. So to comparison with the traditional structure promotion photogrammetry technique, 3D Gaussian splatting benefit is to treat other non-Lambert models like transparency or some metallic reflection models can be generated as a 3D models.
Okay.
Yeah.
Okay, perfect. Thank you so much.
Now you've been waiting so long, so.
Oh yeah, I think my question has been answered. Okay, thank you.
Okay, well that's great. Well, thank you so much.